I'd like to welcome everyone to the webinar series of the Cybersecurity and Information Systems Information Analysis Center, CSIAC. Today's presentation is entitled Learning to Win, Making the Case for Autonomous Cybersecurity Solutions. My name is Steve Warzala. I am the CSIAC Outreach Manager. A couple of administrative notes before we begin. First, all phones have been muted except for the presenters. Questions may be asked at any time during the presentation by utilizing the chat function. Time permitting, your questions will be answered at the end of the presentation. I'd also like to acknowledge and thank our sponsor, Defense Technical Information Center, DTIC. The funding that DTIC provides enables CSIAC to conduct these webinars. It's my pleasure to introduce our presenter for today's webinar, Dr. Robert Wright. Bob is a Senior Advising Research Scientist with Assured Information Security, AIS. He has 15 years of proven experience in developing advanced machine learning technologies that deliver revolutionary capabilities for the Department of Defense. Dr. Wright is a principal investigator for the VICTORS effort, applying his machine learning expertise to advanced biometric verification and attribution. Bob received his PhD in computer science from Binghamton University for his work in developing reinforcement algorithms that learn efficiently from experience. Prior to joining AIS, Dr. Wright was a research scientist with the Air Force Research Lab Information Directorate in Rome, New York, and served as the co-lead for the Autonomy Community of Interest, the Machine Perception, Reasoning, and Intelligence Technical Challenge Area for the Office of the Secretary of Defense. His other research interests and area of expertise include deep learning, data mining, biometrics, multi-agent systems, and genetic algorithms. I will now turn the presentation over to Dr. Wright. Good afternoon, Bob. The floor is now yours.
Awesome. Thank you very much, Steve, and thanks for the nice introduction. So yeah, thank you all for attending, and it's my pleasure to talk to you about a subject that's near and dear to my heart. This is on machine learning and ways of letting it do some really amazing things for control. So I'm going to start off with an overview. So the presentation is going to begin with motivation, why we're all talking about this. I'm going to go into kind of an introduction to machine learning, what it is, what it's doing, and what it can do for cybersecurity, and more importantly, what it's done and where it can go. Then I'm going to talk a lot about reinforcement learning, which is this machine learning capability for learning how to control things, and why I think it's going to lead to some very nice advancements in the future, but also discuss some practical challenges in getting there. And finally, I'm going to end it on some near-term cybersecurity applications I think are kind of primed to do some really cool research in. So with that, let's begin. So the motivation behind this. So unless you've really been living underneath a rock the past 5 or so years, you've probably noticed that artificial intelligence and machine learning
Bob, we've lost your audio.
Oh, am I still on?
Yeah, I can hear you now.
All right. What was the last thing you heard?
You were just getting started about living under a rock.
All right, living under a rock. The past 5 years, you've probably noticed that there's been a lot of advances in artificial intelligence that have been making a lot of news in the mainstream media. Things like autonomous vehicles, Google's personal assistant, Alexa, Watson, and machine learning is the revolutionary technology that's enabling these advances in artificial intelligence. And it really is having impacts across all sectors, not just the visible examples that I talked about before, but behind the scenes. And for cybersecurity, this is true as well. It's already making a lot of differences in there as far as helping us to make sense of the big data, distill all the valuable information that we can out of the data that we're being bombarded with. It's helping us to analyze more and more complex systems and harden them from a security standpoint. And it's just allowing us to make better, faster, more informed decisions given the high speed or rate of which we are being bombarded by data and challenges. However, we're not quite using it to its full potential. And it could potentially do a lot more if we let the machine start doing a little bit more of the stuff that we are still doing for it. The challenge is that it's going to be a little bit difficult, a little bit risky, but the rewards are really going to help overcome and mitigate those risks. So why is this happening now? Why is machine learning all of a sudden seemingly becoming such a topic? And it really has to do with convergence of three factors all coming together at once. The first is the availability of cheap, high-performance computing. And you can kind of thank kids with their video games for this one. The rise of general-purpose graphics processing units that can do a lot of high-speed parallel processing together has really given researchers in the area the ability to do the calculations they need without resorting to going to a very expensive supercomputer. So things that weren't possible before on a desktop are now possible. Second, the emergence of novel models and algorithms. Now, a lot of these algorithms are based on stuff that's been available for the past 40 years, but there have been some new advances such as deep learning that have enabled machine learning to be much more robust, do a lot more than it was able to do before. And finally, the third one is the rise of big data. So with the rise of the information age, data has become much more pervasive. We've been doing a lot more with it, and these machine learning models are very. So now we have enough data to actually feed these things. We have the processing required to process it, and we have the algorithms to do it. And the result is those amazing capabilities that we've seen, which has led to big investments. So in this year, it's estimated that just research dollars, $19.1 billion is going to be invested by private and public sector. By 2021, it's estimated to go up to 50 billion. So before going any further, I figure I'd talk a little bit about what machine learning is exactly. So if you went to Wikipedia, you'd find the definition is an ability to learn without being explicitly programmed, but it's a little bit more than that. So it's any automatic process for extracting knowledge from data, and it requires both generalization and the ability to be demonstrated by the machine. So what am I getting at here? So it's best to go through an example. So let's say you want to use machine learning to help us tell the difference between, or detect malware. So tell the difference between malware and a benign piece of software. So we have some way of measuring the software and mapping it out. So let's say we have a bunch of examples of malware data, things that we've extracted in the wild, and we have a bunch of samples of benign data. And what machine learning is able to do is look at the data and come up with what's known as decision boundaries, so places for making a decision. So in this case, this decision boundary tells us that everything below the area is something that can be considered as benign, and everything above is malware. So that's generalized this type of knowledge. And the way it would demonstrate it is if we are given a new sample, the yellow one there, that is also mapped there, the machine learning model can place that point, use the generalization, and say, oh, because it lies above that point, it thinks it's malware. So that's just one example of machine learning and one type. There are several different types, or three main types of machine learning, and that example is what's known as an example of supervised learning, where the data that the machine is provided has some sort of label associated with it. So the labels back there where we had examples of malware, we had examples of benign software. So supervised is able to use those labels to infer information about the problem. And it requires a lot of the label data. So you may have a lot of data, but unless it's labeled, which can be a painstaking process, it's not really applicable to supervised learning. There's also unsupervised learning, which doesn't require any labels, but because it doesn't have information to go on, it can't do the same types of things. What it is useful for is discovering the structure of a problem, and is useful for things like clustering and pattern recognition. And then finally, there's reinforcement learning, which is semi-supervised. So there aren't any labels, but it's not like unsupervised learning where the computer really isn't giving it any information other than data. It is given a type of feedback signal, which helps it figure out its tasks. So it isn't told how to do things, but it is given some feedback. And it learns from experience. And since it is a topic that we'll be discussing in more detail, I'm going to leave a little bit more of that till later. So moving on, machine learning and cybersecurity. So like as I alluded to before, machine learning is making some good progress in the domain of cybersecurity. So it is being applied right now to types of malware detection, which are much more robust than the typical signature-based techniques that have been used in the past. Insider threat and anomaly detection, it's been very useful for devising some really advanced behavior analysis techniques. For botnet, it's being applied for botnet mitigation systems, being able to detect botnets and come up with ways of getting rid of them. In fact, there's a research called Hacks that is looking at that issue and specifically applying machine learning. And also, so think of your cell phone. If you're using the fingerprint or more importantly, the facial recognition types of authentication devices, that's built on machine learning and different ways of doing it. But all of these systems kind of have something in common in that the humans involved are all making most of the important decisions. All the learning is done offline. The models are trained and then deployed, and after that, they're kind of fixed and aren't able to adapt to changes in the world that they're operating in. Also, the responses, because the humans are making all the decisions, are made at human speed, where they might be able to be done much quicker if we let the machine do it. So that brings us to, we should really invest in autonomous learning. So giving the machine more autonomy to do things. If we're successful in this, we'll have systems that are much more adaptive and robust, are able to respond immediately or very quickly to changes in their operating environment. They'll be much faster. They'll be responding at machine speeds and potentially be able to outmaneuver our adversaries who are looking at using this technology against us. And as I keep saying, this is difficult and a little risky, but the rewards, I argue, are very much worth it. So that leads us to reinforcement learning, kind of the main subject of the talk and the technology which I think is going to get us there. So what is reinforcement learning? So as I said, it's one of the different types of machine learning, and it's one that works off of experiences. So it's an experience-based type of learning system. And it's also something that is applied to sequential decision problems. So instead of something where, let's say we had that malware problem where we have a piece of malware, the decision is just one decision. So is that malware? It's not. Our problem is really done. The sequential decision problem, it's more of like a goal-oriented problem, how to get from point A to point B, how to accomplish some task, or how to prevent something that we don't want from happening, and all the different steps and decisions that we need to make from where we start to where we end. So what it does is it learns a policy which will help us to get there. So the policy, given what our current world is like, tells us what actions we should take to get us to where we want to be. And the way that it's able to learn these policies is by optimizing its model of the world based on the feedback of the experiences that it gets. So on the right, I have an example here of how this could work. So we have a machine that represents our learner and a computer security task where it's going to apply an action to try out to get some experience. That action is going to impact the state of the world, and we're going to get an observation on what happened. And we're also going to get some feedback on whether or not something good or bad happened in the world. And that's going to inform the agent, or this artificial intelligence algorithm, that what's going to tell it, or the observation is going to go to the policy, which is going to help it choose the next action. Now that observation can also be used as a new experience, which can help to refine that policy, which would drive the next set of actions. And then this would proceed in this OODA loop type of thing, continually refining, continually gathering experience, continually getting smarter. So the benefits of this is that you can see that this is an autonomous type of learning. It's able to actually interact with the world and self-optimize its behavior. There aren't any labels. You don't need to tell it exactly what a good action is. From the rewards, it's actually able to infer what the sequences of actions were that led to good or bad rewards. It's adaptive. It's able to change how it behaves over time as the world around it changes, which adds a lot to its robustness. And additionally, the experiences that it learns from don't necessarily need to be from itself. It can learn from the policies of others or by observing the experiences of others. So it doesn't need to learn everything on its own. Okay, so moving on. So it may be automatic and an automatic process of how to learn it, but actually setting this thing up is a very involved process and requires several key ingredients to actually make this thing work. So the key ingredients to any reinforcement learning problem are, first, you need to define what an observation space is, what the machine is going to be able to look at. So if we take an autonomous driving task as an example, the observation space would be things like a vision system that tells it where the obstacles are on the road, where it is on the road, where the pedestrians are, things like the speed limit, and also other things that you wouldn't necessarily be able to see, like what the current speed is going into or the tachometer, things like that. For actions, it's the activities that the algorithm can use in pursuit of the goals. So the things that it can do as part of its policy, for example, would be things like signaling, turning right, and accelerating, hopefully not over some of those pedestrians. And then there would be a reward signal that would give it feedback on the policy that it was following or observing how it performed. Now, it's instantaneous in that it should be given some signal all the time, but for the big events, like let's say it crashed and we would want to reward it or penalize it quite negatively, it wouldn't just learn that last instantaneous action caused that fault. It would actually be able to infer all the way back what sequence of actions led to the bad behavior or what sequence of actions led to good behavior. So it's a very robust system. And it's important to talk a little bit about how it got here and the history of it. So I'm going to spend a little time on that. So reinforcement learning really has its roots as a science, for a computational science in late 80s. But before 2013, it really was kind of making some incremental solutions to toy problems. It had a real problem with scaling up to more realistic problems, with one notable exception of the TD Gammon by Gerald Tessaro's work in 1995. That actually created a world-class backgammon player at the time, which was quite the achievement. But people were really struggling with trying to get it to do anything else at scale. But then in 2013, entered a little company called DeepMind out of the UK. And DeepMind was a small startup that had grand ambitions to create an artificial intelligence, a general purpose artificial intelligence like Data from Star Trek, or something that would really revolutionize things. And they came up with this new machine learning AI technique based on deep reinforcement learning. And what they did was really kind of amazing. They created an AI that played Atari 2600, not just any Atari 2600 game, but all the games. And it was able to play it really well. But so Atari may not sound all that impressive, but what it did was, in that it, instead of spending a lot of time trying to figure out how to describe each individual Atari game to the computer, it had this new system that was able to take what the human player would see, just the raw video, and automatically figured out what was important and what was going on in the screen itself, and what actions it was performing that was leading to changes on the screen, which added a lot more robustness and kind of solved part of the scaling issue. And that was enough to get the attention of Google, who acquired them soon after publishing that in the journal Nature for $500 million. Now, they didn't just take the money and run. They also, in 2014, really came out with, or 2015, I should say, that really shook the artificial intelligence machine learning community. So I remember going to a conference in 2014, and there was this one challenge playing the board game called Go, which is this ancient Chinese board game. And at the time, it was still considered a long-term 20-plus year out challenge for AI. And like chess, it's a perfect information game where there's two players and each player can see what's going on the board. But what makes it way more challenging than chess, and why the chess solvers couldn't solve it, is the size of the problem was astronomically larger than chess. So you couldn't use this traditional search-based techniques that were effective in chess that Deep Blue was able to use in '97 to beat the world champion. So at the time in 2014, the best AI was only working at like a novice skill level and couldn't play the full game. But in 2015, seemingly out of nowhere, DeepMind came out with a new artificial intelligence similar to their Atari AI called AlphaGo, that they said could play the full-size Go game. Like I said before, it used similar techniques to what the Atari bot did. It trained it using watching the experience of professional players playing, and also then refined itself by playing against itself. And they immediately went to challenging experts, and on their they were able to defeat the European champion in a match 5-0, which got a lot of attention and led to kind of an event where they challenged the reigning world champion at the time in 2016, Lee Sedol, who was very confident that he would beat this machine, but he might let the machine at least win one game. Well, things didn't work out so well for Lee. He lost that match 4-1 very convincingly. And he did remark that the one time he did beat the machine was the most proud he had ever been in his play. So that was in 2016. In 2017, they made more progress with this new algorithm. They changed it a little bit, so it was a generic board game playing AlphaZero, and right now it is the best at Go, chess. It beat the traditional chess playing programs and shogi. More recently than that, not DeepMind, but OpenAI, Elon Musk's team has been making a lot of progress in playing games and more tactical games. But the humans are still a little better at that point. But bottom line is, don't challenge your computer to a board game anymore. They've got them licked. So that's a little bit of the history. Why is it working so well in games? Well, there's a bunch of reasons for that. For games, there are these problems are very well-defined problems. The rules are all set. All the observables, everything that you can look at on these games is very well understood. The actions, the interfaces, it makes it somewhat easy to apply these algorithms to. They all have very nice optimizable feedback. So there's a very easy goal for the reinforcement to work with: win the game or score as many points as possible. So there's not a lot thought that needs to go into devising a good feedback function. And most importantly, they're all virtual simulations. So reinforcement learning and our machine learning requires a lot of experiences. Simulation is a good way to get the experiences, and the simulations match the target environment. It's the same exact thing, and there's no risk. If you lose a game, there's no big deal. Massively parallelizable, you can play tons of games all at once and learn lots of things and apply it all to your policy. So yes, we can get a lot of experience, and that's really kind of the advantage of why games have been so prevalent. So there's some good news on this and how it relates to cybersecurity. So cybersecurity, a lot of the problems in this domain kind of share some of the same aspects of a game that would also lend these problems well to being solved by a reinforcement learning solution. So one, a lot of them can be simulated. They exist in a virtual world, and they can be simulated, processed faster than real time, and what's being simulated matches up well with what can be experienced in the real world. So these things can be done at low risk, and we can get a lot of experience relatively inexpensively. Also, another good thing is in a bunch of the cybersecurity realms, actually breaking things, which is not necessarily good in a lot of domains, can be a really good thing. So there's a little less risk in actually trying different new things to get the experience you need. These domains can be adversarial, which doesn't necessarily sound like a good thing for an environment to have, but it actually can be, because the adversarial component of it can force our learning component to try different things. It'll actually drive exploration, force it to learn new things about the environment that it wouldn't necessarily see unless it was forced to. And also because we learn things about what we're potentially vulnerable to as an adversary, we can look at it from the adversarial standpoint and figure out ways to harden our system. So there's a dual purpose to the adversarial component that reinforcement learning can take advantage of. And finally, a lot of the problems have easily defined rewards. So we don't have to think about too difficultly how we're going to define the reward structure. We can use things such as like the threats detected that gives us a very easy gradient to follow to improve how the machine is performing. We can measure how it's performing. We can look at things like disruption, utilization. So there's a lot of good ways to measure how these machines are performing when they're learning how to interact with the environment. So that leads us to the practical considerations, challenges and pitfalls in actually accomplishing this. So yes, cybersecurity is primed for it, but it's not that simple. It's not, we can't just go ahead and do it. There's some things that we need to consider. First and foremost is defining problems, actually describing what the problem is to the machine is a very, very difficult task. This is something that a lot of people are working towards making computers better at, but still it's a very manual task and computers are exceptionally dumb. And actually doing this task is very easy to mess up. So I got a couple examples here. First, we can very easily overspecify the domain. So the top example here is one in which I've set up. We have a car on the lower left. It needs to navigate to the goal that's in cell 7. We've defined each cell as a different state that the world could be in, 1 through 21, and we need the car to figure out a policy to get from where it is to the goal. So because we've actually, so if we can let it loose and let it learn and learns a policy that follows the green arrows, but because we've kind of said like each cell is its own thing, if we change where the goal is, so move the goal from state 7 to state 19, this policy is no longer valid. It won't get us to 19. So we have to go through the process of learning a whole another one and throwing out everything that we learned. So we've really just solved one instance of a much more general problem, and we can very easily do that. The other side of the spectrum here is that we can also easily underspecify the problem. So we still have this car, we give it all the sensors that it needs to know where it is in the world, but if we don't tell it a little bit more, we could say like, hey, navigate to Rob's house, and then it could respond, if we're lucky, with who the heck is Rob, because we haven't told it what or where Rob is, where it is in relation to where it is, and this car could go off and start wandering looking for a solution to this problem. Maybe happen upon Rob sometime from now to infinity, but really it makes it kind of a hopeless learning problem. So we need to find the right balance between specifying exactly what the problem is, but giving it the leeway and understanding and making sure we're solving the more general, broad problem that we're really interested in solving. And to do this right, it really requires extensive domain expertise, so that we know all the fine detail of what makes this problem the problem that it is, the interesting points and complications. Solve the more general problem we're interested in solving. And if you don't have both of those ingredients, it's not going to happen. But if you do have both of those ingredients, then the process of actually describing the problem comes down to defining what's known as a Markov decision process. And this is 4 basic components: state space, action space, reward function, and discount factor. The state space I alluded to earlier, which is this observable space. When you're designing that state space, it's important that you keep it pertinent to only the features, the things that are important to the environment and nothing else, because it just drives up the amount of experience and complexity of the environment that is going to slow learning and make it not as robust. And from what DeepMind has done and what we're seeing a lot right now in research, deep learning really helps with defining this. So if you were going to define your own problem, certainly consider using deep learning. For action space, we want to enumerate all the valid actions that the machine could take in doing this goal. But again, we want to keep it concise. Again, this can complicate the problem and increase complexity, which can seriously slow learning and the overall learnability of the problem. And finally, or not finally, next is the reward function that describes whether or not the machine is, or I should say the policy is performing well, good things, bad things, or neutral things that it can do in the environment. And this is where, if we're not careful, we can get things where to save humanity from suffering, the best way of accomplishing this is actually to remove humanity. It's important to define the function so that you don't get any of that emergent behavior that you don't want out of the system in there. So that's an important piece. And finally, the discount factor, not really something that needs a lot of thought about, but it does change how the system will behave by adjusting how much it wants to get immediate rewards versus how much it wants to actually play the long game and solve the long-term problems. Okay, so another consideration while designing or thinking about applying reinforcement learning to a problem is something, or is how are you going to get the experience that you need to train this system, or how is it going to get the experience it needs how to perform in this environment? So there's a rule right now, needs a lot of data, and reinforcement learning is not an exception to this by any means. So going back to the AlphaGo example, that required 30 million moves of pro play to watch, and then thousands, if not millions, of games of experience in order to get to a professional level. And these experiences can be very expensive to get. Simulation is nice because it reduces a lot of that cost, but it doesn't necessarily get rid of the costs. And not only do you need good positive examples of experiences, but also you need some negative experiences. So the positive or the negative can be just as important pieces of data as the positive experiences, because it really informs the algorithms as to what not to do, which you really want the machine to know. So in designing it, you need to figure out where you're going to get your data from. You can use simulation, which is very nice, but you may not get the fidelity that you need that matches up with the real world that you're working on. You can let it learn online, or at least observe online. So that being watching during actually trying to accomplish the actual task, whether that be in a virtual environment like a cybersecurity world or a physical domain. Physical domains like robots or automated vehicles, things of that nature, are another online domain that you could try, but the cost there can be a lot more, especially when getting negative experiences. If things fall over or break or crash into things, there's a lot of cost in that to get the negative experiences. So you're going to have to figure out how to do that in physical domains. So if you can, simulation really is the best option for getting it. You have to worry about the fidelity, but there are some ways to kind of mitigate the risk for how you're going to do the collection. So you don't necessarily have to do fully autonomous exploration where you let the machine try different things. You can also, there are also other techniques such as learning from demonstration, where instead of actually giving the computer the controls to start out with, you actually gather experiences by observing how a human would do it, or how a heuristic, so something that we programmed before that can accomplish the goal, how it would do it, let the machine observe these experiences, and then infer the policies that would work well in that environment. It could even, if it observes enough different entities doing it, it can learn how to do it better and even inform people where they're doing things wrong. So it's something to consider. And another major challenge to actually trying this out is trust and autonomy. And this is both a technical and non-technical test. So when is it appropriate to actually give these things control of a system? When are we actually comfortable with doing this? So from a technical challenge standpoint, this has to go, or this has roots in control theory, or where we can actually test how machines are they going to do what we think they're going to do, or what we're going to bound them to do. And unfortunately, the stuff that the formal verification methods that have roots in control theory don't really apply to these adaptive autonomous learning techniques, because the question of how are we going to ensure something is going to do something that it's not explicitly programmed to do when the system is supposed to do things it's not explicitly do is a fundamental problem. So a lot of smart masochistic people, are much smarter than me, masochistic people, are working on this, but it's not quite there yet. So the other option is to do exhaustive testing of these systems. And this is what the autonomous car makers like Waymo, Uber are trying to do right now. But it is expensive. It can be dangerous, as what we've seen with what Uber has done. And it doesn't really offer any guarantees, particularly for these systems that are going to be learning online. So if any change in the system, that testing has to be redone. So we still need some more testing processes to really, or refinements in the testing process to get the job done there. And then there's also the non-technical challenge considerations that you have to do. So there's quite a bit of skepticism with these new things, people not really trusting, are getting really nervous the first time they take their hands off the wheel. They have their own personal biases. They can definitely do it better than the machine can. And then there's the fear of, I don't know what this machine is going to do. We haven't really bounded what it's going to do. So what are the answers to this? And that's a tough one. But so this is a personal feeling, or opinion, I should say. But with time, these learning systems are here to stay, and they're going to have to gradually earn our trust. And over time, I think we're going to achieve more and more acceptance in what we're actually allowing these things to do. And as we get more comfortable, it'll just get more and more. It's important to note that technology is improving very, very rapidly, which will help to speed this along. So our algorithms are getting significantly smarter and better at a monthly basis. So a lot of the challenges that I've brought up now won't necessarily be a challenge tomorrow or the next day. Also, the testing and validation process are getting considerably better. Google, Waymo are pioneering the validation processes. We're going to learn a lot more from that and get better at it. So my advice is to just continue to press forward on this, be very thoughtful on how we do it, be responsible, be brave, and live boldly. So there's going to be some risks, but the payoffs are going to be quite revolutionary. So with that, I'm going to move on to noting some near-term applications that I think in the cybersecurity space that have the potential for very near-term application and success. So I'm going to start out with the first one, which is autonomous red teaming. So letting the machine actually help us with how we're doing red teaming. So the problem of red teaming is, for any particular software or network system, devising a comprehensive set of tests that could evaluate the security or robustness of a software system. So taking a software system or network and figuring out security holes or getting it to perform behaviors that it isn't intended to do. And so this is a task that is in quite high demand. But the issue with it is that in order to do this, it requires very skilled professional hackers, for lack of a better word. There aren't enough of them out there to really handle the demand that's out there. And also the skill sets of them vary quite significantly from one to the other. So there's a little bit of change, or a little bit of issue with how comprehensive the evaluations they can perform. Additionally, the software systems that they're being tasked with are becoming there's increasingly more numbers of them, and the systems themselves are becoming increasingly more complex. So the amount of time it takes to do an assessment of the system is becoming much greater and much more difficult. And then, as I talked to you about before, consistency in these evaluations is an issue. We need better consistency in standards. Not all evaluations are created equal. So if we could devise a reinforcement learning solution, it could help us in that it could provide a system that could aid the the non-hackers or the least skilled actors, and by giving them advice, by observing how the skilled ones perform across a wide variety of tests, and basically create a super intelligence that could help and guide them and train and augment the evaluators that are out there. It will also provide a scalable intelligent solution, so something that can meet the demands of this increasingly pervasive, increasingly complex set of systems. It can be automated, parallelized, and adapt to changes in how it works. And finally, it would help to provide, if we had this, like everything was kind of learned, and essentially it can provide a more consistent evaluation process. It could learn from the experiences from everyone and augment those experiences and fill in the gaps and skill sets of people who are trying to perform their function. So some more of my opinion of why this will work well. One, actually performing the assessments can be done in a very low risk environment. You can simulate things and also give it a lot of license to try a bunch of new things, because if it breaks something, it's kind of accomplishing the task that it was set about to do. So there's no risk in trying something that would break another type of online system. So we want it to explore, we want it to do risky things in the what we consider risky things. Tasks that you would do, things like fuzzing in an assessment, are episodic tests that a bunch of the knowledge can be generalized. So you can create models that, so you would be able to learn effectively from one assessment of one system to another. So there are things that can be learned by a machine learning system that would apply to different contexts. And these, it can also be done at scale. So we could have a system that is aiding a bunch of different actual operators that are doing the things, get and learn from all these different areas, and give us the experience that's necessary to train it and also become effective somewhat quick. But there are some challenges associated with actually doing this, and the primary one is the ingenuity behind the reinforcement learning systems. The machines in general still, the reinforcement learning still lags humans in being able to come up with complex or analyze complex relationships across different domains that really leads to some of the more interesting edge cases of things that you would discover in a vulnerability assessment. And the machines can't really be relied upon at this time to really discover those things. So in deploying this, it might be best to look at kind of a mixed initiative deployment where it's the machines and the humans working together, and as a team providing a better service. And then the next, or I guess the final our near-term application is dynamic maintenance scheduling. So keeping our IT systems running smoothly. So for any organization, we have our computer that runs on computers. We have this problem, our IT people have this problem of designing maintenance schedules for patches, backups, system scans, upgrades, etc. And they have to do it in such a way that maintains our effectiveness and our security posture, while also minimizing downtime and disruption. So we need to be able to accomplish our mission and stay secure, and do all the things that are necessary for that. And these are conflicting things. So issues with this is that if we're going to create this automated system, or not autonomous system, trying to do it is complicated because organizational needs vary from one to the other. They are constantly in flux. So day to day, month to month, their needs, their missions are constantly changing, and threats, as well as the missions, are also evolving. So this is a very dynamic problem. And we also have to deal with intelligent adversaries that are actively trying to figure out ways of disrupting us, breaking down our security, or impacting our missions. So what a reinforcement learning solution could provide that other systems can't is really customized solutions tailored to the organization. So it can adapt itself to those individual organizations to provide maximum effectiveness and minimal downtime. It can really provide what's known as an autonomic system, so a system that can respond dynamically to different problems that may occur seamlessly, and it can help us to outmaneuver the adversaries and the intelligent threats. So breaking down our adversaries that we know of. So again, why I think this will work. So one, schedules are policies. So reinforcement learning in the gaming domains and other domains has shown that they are very effective at devising policies for complex and dynamic adversarial environments. So it's the same thing. It can do it in the games. It should be able to do it here. There are very good optimization metrics, like I was saying before, with cybersecurity domains. We can look at things at utilization, uptime, downtime, things of this nature, which would tell us whether or not our system is performing well or bad, which would lead to better and better behaviors. And the problem really in itself does demand an autonomous solution. Our IT people are pulling their hair out trying to deal with the response times necessary, and it really requires a constantly maintained adaptive process. So it's really, the problem wants this type of solution. So, but the challenges are, this is not necessarily something that can be simulated effectively. So a lot of the learning will need, particularly if you want to do adaptation, will need to be done online, and we can't let the machine try new things necessarily. The system can't go down. So unless it's sure that this is a safe thing to do, we can't really let it learn or try different things that could lead to catastrophic failures. So we could augment this by bounding what the machine could do with some certain rules that could kind of just help aid it in ensuring that it's not going to do something exceptional. It may limit the novelty of the solutions that it can come with, but it would prevent it from doing catastrophically bad things necessarily. So with that, I've said a lot very quickly, but in summary, I hope that I've made a good case for why machine learning is incredible, and particularly why reinforcement learning has a great potential, particularly for improving cybersecurity and ways and why it's a good fit for cybersecurity. Hope I've kind of informed you on some of the interesting challenges, and that there's a lot of potential there, but getting us to where we want to be is going to be challenging and expensive. There will be some failures along the way, but to the people that make it through, there will be also some very rewarding and really revolutionary capabilities to come out of it, I believe. So with that, I think we're ready for questions. I'd like to finally add some special thanks to CSIAC and Quanterion, particularly for their patience in me developing this material. A benefit of being a machine learning expert in cybersecurity is that we're very busy, and they were very patient with me. So thank you very much, and thank you for your attention.
Well, thank you very much, Bob. That was a informative presentation, and it's it's one of these cutting edge technologies that I think is really going to make some big changes and big impacts. So see, I'm gonna try to go back. We've got a couple questions here. All right. So the first question that came in had to do. It was on the slide. When you were talking about the trust and autonomy, and in the technical challenges portion, there was a question about how you go about estimating positives versus false negative examples. Do you have an idea on how you deal with those situations?
So how you go about estimating? So that gets along to in a supervised learning aspect, like, you're going to need a training set that tells you the labels you're going to need a training set with the labels, and you need a testing set. The testing set will allow the machine to learn something, and then you need to verify it using the testing set. And unfortunately, you're going to need a lot of labels for both, a lot of data for both, and labeling that data is expensive and needs to be done right now manually. There is a lot of research being done right now in actually using the machines to automatically label data in one domain to another that's showing a lot of promise, and might help alleviate the problem of having to come up with a lot of good labeled data. But it's still research, and right now you need very large data sets that are meticulously labeled.
Okay, thanks for tackling that one. We've got another question dealing with policy, and the individual is wondering if it's always decided by humans, or can the policy be autonomously updated by the machine? I guess I would think that the policy is a human-driven thing, but you can let us know your take on that.
All right. So the policies that I was talking about is actually the machine's understanding of the problem and how to act. So the machine would update its own policy. This wouldn't be like, this wouldn't be like the rules policy that the humans would dictate. But it could be, machine policy could be augmented by a human defined policy, so that we get away from those situations where the machine learns something and it would want to try something that the human policy would say absolutely. So that there's a place for both. But yes, the machine would be updating its own policy based on the data and the experience.
So now, would it be possible? So given a defined policy, and the machine goes out and is learning things. Could you see a situation where the machine might come back and say, if you change to telling the human, suggesting to the human, if you changed your policy, I could do this better, or do you see that? Could that be possible? That kind of augmentation?
Absolutely possible. So the policies that it has are based on the value. So the amount of reward, so based on that, the performance metrics, how well it's expected to perform if it follows X action as opposed to Y action, and continues doing that until completion. And then there's other work, particularly out of CMU, that's looking at things like that are called explainable AI, where it would be able to take something that's more of like just a number saying this is why I chose thing, and actually come up with a human understandable explanation as to why this decision is the one you should take. So there's definitely work being done there, and it's getting better to the point where it could actually explain to you in English why this is the best decision.
Okay, great, thanks. Let's see, there's a comment from one of our attendees on the policy question that I'll just there's suggesting that it would be helpful to compare a firewall policy, which is a rule set, versus an operational policy as defined by an officer of the company. So just kind of a comment on that policy discussion as well. So okay. Let's see. Here's another question. Another question that we had is why is it that reinforcement learning can greatly improve cybersecurity, and can you comment on the correlation between these two aspects, between the reinforcement learning and the cybersecurity?
So I'm not sure about the second part, but a lot of I tried to emphasize that the reinforcement learning can provide a much more tailored and robust solution that it will continually improve either our ability to accomplish our mission or our security standpoint dynamically as threats evolve, as our missions change. It can learn dynamically based on how things are changing. I see it as a big thing, and it can also help to create policies that are either more permissive or less permissive based on the nature of the work that an organization is performing, things of that nature. So much more tailored solutions.
Thank you. We have another question. It's folks are so many cybersecurity concerns, are not well defined in practice, and the example is, monitoring in an organization's ecosystem. So how do you think the autonomous cybersecurity problem can be framed to deal with that?
So that's a very large problem, and it's probably best to look at small problems and build a whole solution up from that. It can. So I don't think that applying it to control everything all at once is the best route, I guess. Not sure if I'm answering the question adequately, but trying small niche things might be the best way to get started, and then building up.
So kind of your bottom up or modular, and kind of grow it from there.
Yeah. So that's what I'm getting at. I'm not sure if I'm answering the question that was asked though.
Okay. So I had a question on, when you were talking about the red teaming, which does seem like an ideal an ideal approach. I guess the thing I wanted to clarify is, it's good good to break things in that case, but I guess are you running it on a real live system, or are you running a simulated system, or the live system in a sandbox environment? Because it's one thing to let your machine learning go on it, find the vulnerabilities, but then if it's breaking the live system, that could be.
Breaking the live system is a bad idea. So yeah, you'd probably so just like any red teaming assessment, you'd want it to be either sandboxed, but still representative of the actual fielded system if it is indeed fielded, and particularly if you're doing a continuous assessment. You wouldn't want something that would hurt either your user experience or your customer experience, but at the same time, you do want to see where it's going to break. So doing that in a safe space, like a sandbox, is the way to go.
Okay, great. I assumed that was the case, but just wanted to make sure.
Yeah.
Okay, we've got another question, and they're asking if there's a limit to the reinforcement capacity of the algorithms. For example, if you pit a blue team algorithm against the red team, would it sound as if it would eventually exhaust all actions until a clear winner emerged?
So if it's a red versus blue zero-sum game, it could converge to some safe point, like something that we would think of like game theory. In terms of capacity to learn things, it depends on the models that you're using. So the neural networks or whatever you're using to model the world and encode your policy, depending on the complexity of that, can change, how robust or complex a solution you can have. One thing about that, though, that I alluded to is that if you have an ever-increasing model, it does increase the amount of experience that is going to be required to train and learn, or the amount of experiences you're going to need quite significantly, if not exponentially. So you're going to want to make sure not to create the most complex model at first. You're going to want to start simple and build up to it. And yeah, it could, for whatever solution your whatever domain it's being applied to, it could learn an optimal convergence point potentially, but depends on the environment.
Okay, great. I appreciate the answer to that. So we're kind of running near the end of the time, but I had kind of one just question. You had some early slides, talking about the work with the autonomous vehicles and things of that nature, and there's been great advances, great strides made with that. But I guess, well, we're both up here in the upstate New York and in the Northeast, and our winters, we get some, we can get a few feet of snow and some.
Yeah, I know where you're going here.
Yeah. So what happens like in a blizzard whiteout? What does an autonomous vehicle do in a case like that? What's going to happen?
What does it do in a case like that? So it's certainly going to need to be tested exhaustively. But this isn't really necessarily a reinforcement learning type of issue or problem per se for the perception, but there's some really, really amazing work out of, I think it's UPenn, or I'm not sure, that was recently published that showed that it can actually remove what you would consider like whiteout conditions, can remove the snowflakes and show a dramatically clear image of what's actually there. I forget exactly what's going on underneath the hood, but it's amazing what machine perception can do right now, and it's getting really good. Right now, it's not a false statement to say that computers are better at recognizing doctors' handwriting than people are. It can read things better than people can. So machine perception is making tremendous strides.
Okay, so there's a possibility that it would actually do better than us in those conditions, given the different sensors that it has on board. So.
Yep, as long as they test it right and you feel comfortable taking your hand off the wheel.
Yeah. Okay. We've hit most of the questions that came in right now. But so, if folks want to, folks have questions after the fact, or, something, pops into your head later on, Bob has his contact information up there, or you can send us a question here at CSIAC at, info@csiac.org, and, we can get it to Bob. And Bob, also, I mean, if you do get questions on this, topic from other folks, if they send them to you directly, if we have our tech forums on the CSIAC website. So if you do get questions, if you'd be willing to share it with other folks, to expand it out to the community, that we'd appreciate that too. So, and once again, I want to, thank you for taking the time, sharing your expertise, your experience. I think you kind of created I captured a new word that you may have created or tried to create. Expertarians is a new word I'm going to use.
Oh, no.
I like that. I'm gonna use that. Expertarians. So once again, I really appreciate it, and it was a great presentation, and just thanks for doing it for us. We appreciate that.
Thank you very much for inviting me, and thank you all for your attention.
All right. Well, I'd like to thank everybody for attending, and I'll make a tentative announcement. This is kind of happening in real time, but I think we might have our next webinar on the 20th of September. Like I said, still TBD, but we're hoping to look at some computer game technology. We're looking at a model-based approach for a game-oriented approach for mitigating cybersecurity risks. So hopefully that'll happen on September 20th. But we'll send out an announcement on that. So we'll keep an eye out for your in your email, and we'll let you know when it actually gets firmed up. So that's it for today. Thanks for joining us, and we'll hope to see you next month. Thanks a lot. Bye bye.